Hey guys, hope everybody's doing okay. This is Mr. Krowski. Today we're going to take a look at a short summary lesson on Coulombic attraction, Coulomb's law, and effective nuclear charge. So there's a much longer video in this playlist that goes into a little more depth on this, but this will be a quick summary of that and just focus on some main components here, and we'll learn how to prioritize, like how to figure out what atom or ion has a stronger attraction to its valence electrons that we'll get to towards the end of this. Okay, so let's focus on what Coulomb's law is. So here's the official definition. And there are really two components, two parts that we need to worry about here in Coulomb's law. So it tells us the strength of the attraction between two charged particles. So your charged particles are your nucleus, right, with your positive charge, and your valence electrons, which are negative. The strength of attraction between them depends on the magnitude of the charge, so how big that charge is. You know, is the nucleus a +3, is it a +4, +5, whatever. And the distance between them, the distance between the nucleus and the electrons you're talking about. Okay? So those are the two components and two parts of Coulomb's law, but which one's more important? Which one makes a bigger impact on attraction? That could be determined by looking at the Coulomb's law equation. Okay, so you don't really need to like memorize this, but you need to look at it and be able to figure out what is making a bigger impact here. So the attractive force is equal to K, which is some constant, multiplied by the charge of part 1 times the charge of part 2. Those are your two particles there, your two like parts. And that's divided by your distance squared. All right, that's important. So if you look at this, what part of it do you think is going to have a bigger impact on that attractive force? Well, it's going to be your distance, okay, because you're taking your distance and you're squaring it. So if you double your charge, say you double your charge from 2 to 4, now you're just doubling it, right? But if you double your distance, you have to square that now, okay? So it has a much bigger impact on your force. So if you triple your charge, you're tripling what you have here in the numerator. But if you triple your distance, now you're tripling that squared. Okay, so now it's a factor of 9 that you're changing this force by when it's in the denominator there. So it's going to be a much bigger impact when you focus on distance, and I'll try to show you that in the next couple slides here. Okay, so you really need to focus on trends in attraction going down a column and across a row. Let's take a look at those one by one here. So we're going down a column. We have lithium, sodium, and potassium. I have the electrons all on the screen here for you. And it's focusing on, like this question here, is focusing on the first level electrons, those 1s2 electrons for all three atoms. So if these electrons, you know, those 1s electrons, if they're the same distance from the nucleus, would they have the same force of attraction? Well, let's take a look at our Coulomb's law here. The distance we're saying is the same. Okay, they're all in level 1. So let's say it's 1 squared. Okay, so the denominator here is the same for all three of these. So does that mean you're going to have the same attractive force? Well, no, not necessarily, because look at the top of this. We have to focus on the charge of part 1, which is the nucleus, and the charge of part 2, which are the electrons you're dealing with. Well, we're dealing with 2 electrons for all of these, those 1s2 electrons. Well, what's different then? Well, it's going to be the charge of part 1, the charge of our nucleus. Lithium has a +3 nuclear charge. Notice I'm not saying effective nuclear charge, I'm just saying nuclear charge. The nuclear charge is simply the charge of your nucleus, which is the number of protons, right? Sodium has 11, so it's a +11, and potassium is 19, so it's a +19 there. So you can see that potassium has a stronger hold, a stronger attractive force on its first level electrons than sodium or lithium, okay? Because of the Coulomb's law formula, right? And the difference in the charge of part 1. The charge of part 2, same for all of them. Distance, same for all of them, because we're focused on those inner shell electrons. Now, if I change this is important, and I said let's focus on the valence electrons, Well, now look, your valence electrons in lithium are in level 2. So your distance would be 2 squared, which gives you 4. For sodium, they're in level 3, right? So now your distance is 3 squared, which is 9, okay? Which is going to make your force smaller because your denominator now is a 9. Look at potassium. If you're focusing on the valence electron, it's in the 4th level. 4 squared is 16. Now you're taking your numerator, dividing it by 16. You're getting an even smaller force. So the force of attraction with potassium, like for potassium, is way smaller for its valence electron than it is for lithium. If we're focused on the inner shell electrons, though, it's stronger. Now, most of the time, you're going to be focused on those valence outer shell electrons, okay? A great deal of the time you are. But, when we looked at PES, photoelectron spectroscopy, we're not always dealing with those outer shell electrons. We can have, ionization energies for all the electrons in an atom. So it's just important to understand why the ones in potassium for the inner level are much higher than lithium or even sodium, right? So here we are. We're focused on valence electrons now. So moving down a column, you only want to focus on number of energy levels. That is massively important here. So number of energy levels dominates. While there are definitely more protons going down, more electron repulsion, more energy levels, right? They are further away. So that creates less attraction between the nucleus and your valence electron. So the trend in attraction going down a column is super easy because you focus on energy levels only if you are focused on those valence electrons, which is what you usually are focused on. Okay? So those are the same nuclear charges as before. Now, let's go across a row. Let's look at something a little different here. So we're going to find the effective nuclear charge. That's the net charge of the nucleus felt by an electron. So if I just go back real quick, potassium has 19 protons. That outer shell electron doesn't really feel the pull of all 19. Okay, so what we're going to do is figure out what does it really feel the pull of. Okay, that's what an effective nuclear charge is. It's represented by Zeph. All right, Z is the nuclear charge of the nucleus. Then the EFF is effective. So Zeph is effective nuclear charge. So true or false? You have the Zeph of the electrons in B, right here, helium, is twice as much as the electrons in A. So let's take a look at it. So A has hydrogen, okay, it's 1 proton, and helium has 2. So would you think that helium, those electrons here, feel twice as much pull, twice as much attraction as the hydrogen electrons do? It would seem like the answer to that is obviously true, but we're going to find out that it's actually not. So here we go. You don't really need to calculate Zeph. Some students get themselves in trouble here. They try to calculate Zeph, they screw it up, and they get the part of the question wrong. If you could thoroughly explain this without formally calculating Zeph, then that's fine, okay? But sometimes it helps to calculate it, which you saw in one of the previous videos. Okay, so the effective nuclear charge is Z, which is your number of protons. That's your nuclear charge. So for letter A, here, Z would be 1, and for B, Z would be 2, okay? Twice of ZA. So Zeph is Z. Now you have to get rid of the shielding, okay? So here you have 1 electron. Do you have any shielding electrons in A? The answer to that question is no. Look at letter B. You have 2 valence electrons. Are there any shielding electrons? No. There are no electrons between the valence and the nucleus. The valence electrons are the only electrons here. This is a very simplistic example. So the shielding electrons for both are 0. So we have basically 1 minus 0 and 2 minus 0. So you're like, all right, well, 1 minus 0 is 1, 2 minus 0 is 2. Sure, it looks like the effective nuclear charge of B is twice that of A. But there's one other thing we have to look at here. The other thing we have to look at is something called a repulsion factor, okay? Electron repulsion weakens the effective nuclear charge, okay? So here we have no electron-electron repulsion. So we basically have 1 minus 0 minus 0. Okay, so the effective nuclear charge for this electron is 1. Okay, it feels the pull of that 1 proton. But for B, we have some number. Like, you don't have to know what it is. You can look it up. They're all over the place. And this is where it can get a little tricky. But because you have 2 electrons here, they're trying to get away from each other, right? There's some electron-electron repulsion here. So it's going to be some like small decimal number. Let's say it's like 0.2. Okay, I don't know what it really is. So we have 2 minus 0, which is 2, minus 0.2. You'll get something like 1.8. You know what I mean? Like 1.86. I don't know what it is. But because that R value is an actual number here, we don't have a complete doubling of the effective nuclear charge of A. Okay? So even though the charge is doubled and shielding is 0 in both cases, the electron-electron repulsion of the other electrons in the outer level reduces the net pull of your nucleus. So atom B does have a much stronger attraction. Let's not get that mixed up here, but it's not quite double. So letter B, like that atom, is still smaller than A. It still has a higher effective nuclear charge. Okay, it's just not exactly double. Honestly, a lot of the time you don't have to worry about that R. You can just simply because say it is such a small decimal. Okay, the effective nuclear charge, the Zeph of B, is like 1.85 or something. Well, it's, for all intents and purposes, we could say it's 2, right? So a lot of times you can see that R value is kind of negated or not shown, and you have Z minus S. I want to say that might be how it was in one of the previous videos. Okay, so you could say the effective nuclear charge of A is 1 and B is 2. Just know in reality it's a little bit smaller than 2. Okay, so going across a row, let's take a look at this real quick. You have carbon, nitrogen, and oxygen. How does the Zeph compare for these? Let's figure it out. So the effective nuclear charge of those, to figure that out, you need to know what Z is. Z is the number of protons. That is 6 minus something. Here it is 7 minus something, and here it is 8 minus something. Okay, effective nuclear charge is nuclear charge minus shielding. So here are your valence electrons. You have 1, 2, 3, 4. You have 4 valence electrons in carbon. You have 2 shielding electrons. Okay, so 6 minus 2 gives you 4. All right, we're gonna forget about that repulsion factor because I don't know what it is for these. Okay, it's not gonna make a huge impact. So here you have 7 minus 2 gives you 5. All right, because we have 2 shielding electrons and we have 5 valence there. And then we have our 8 minus, again, 2 shielding electrons. Gives you 6. Okay, so the Zeph of carbon is 6, the Zeph of nitrogen is 7, and I'm sorry, the Zeph of carbon is 4, the Zeph of nitrogen is 5, and the Zeph of oxygen is 6. There we go. So you can see that oxygen has a greater attraction. Its valence electrons have a greater attraction to the nucleus. Okay, you could figure that out formally by finding Zeph, or you could think it through. How do your energy levels compare? Well, all of these, the energy levels are in level 2. Okay, so two levels. So energy levels, it's a tie. You don't worry about it. Anytime you're comparing elements within the same row, you're not going to worry about number of energy levels. It's going to be a tie. All right. So what do you focus on next? The next thing you focus on has to be the number of protons. What is that nuclear charge? Okay. Shielding is not going to matter. Okay. Because you have 2 shielding electrons for all of these. If you're in the same row, your shielding electrons is going to be the same for all of them. Okay. Because of, you just look at your electron configuration, right? You always have that same core, and then your valence is what is changing. And electron-electron repulsions not making much of an impact here. There are times where that does make an impact, not necessarily in this example here. Okay, so how does the size compare for these? If oxygen has the strongest Zeph, the strongest effective nuclear charge, these valence electrons are being pulled in more, right? So oxygen will be smaller, carbon will be larger. So moving across a row, left to right, the atomic radius gets smaller. You cannot explain this in this AP course by saying it gets smaller because it moves to the right, okay? That's not why, okay? If I have somebody that's really short and they stand next to me and I say, why are they shorter than me? You can't say, well, because they're standing next to you, okay? That sounds ridiculous. You have to explain why, like genetics, you know, male or female, whatever, you know what I mean, age. Those are the things you need to talk about. Same thing here. You can't say, oh, it's because it's to the right or to the left. You have to explain it in terms of attraction. Explain it in terms of nuclear charge or effective nuclear charge or energy levels. So we'll practice on forming those good answers so we know how to answer those things properly. Okay? The electron-electron repulsion is more here because you have more electrons, but it's not making a huge impact on that number 6. So here's your trend. Atoms get larger as you go from top to bottom, not because you go from top to bottom, but because you have an increasing number of energy levels. And the size decreases left to right, not because it goes left to right, but because you have an increased nuclear charge and effective nuclear charge. So this should say 4. Okay, I added 1 at the last minute and forgot to change that. This is something you need to commit to memory and use literally every single time you think of anything in terms of attraction or periodic trends, okay, or ionization energy. This is the key right here. Like, you will not make any mistakes. You cannot go wrong if you go off of this priority list first. So the factors that affect attraction the most significant is an energy level, okay? If something's in level 4 and something else is in level 2, it doesn't matter about anything else on this list. Level 4, further away, will have a weaker attraction than something at level 2 or 1 or 3. You know what I'm saying? You will only need to go into the rest of this list if the energy level is the same. So you only focus on this stuff here if the energy level is a tie, okay? Literally, do not go past number 1. If it's a tie, you don't need to. Students get themselves in trouble there too. They go through all this rigmarole explaining all this stuff when they simply need to focus on the number of energy levels something has and how that affects your nuclear charge or your effective nuclear charge and your attraction, really, okay? So let's say the energy levels are a tie. The next thing you look at that's most important is your nuclear charge. That's your number of protons, right? If that's different, then you're done. You stop there, okay? If that's a tie, right? Say you have like oxygen and oxide. So you have O and you have O minus 2, okay? Well, now your nuclear charge is the same because they're both oxygen, but one's an ion and one isn't. Now you go into shielding, which you're really not going to use much because the core electrons will be the same because we're in the same row here. So you would go with electron repulsions there. Okay? So a good example of this is exactly that. If you have O and you have O negative 2, okay? Energy levels, tie. Nuclear charge, tie. Both have 8 protons. Shielding, tie. What's left? Electron repulsions. Oxygen has 16 electrons. Okay. Oxide has 18. All right. So there are more electron repulsions here. Okay. So there are more electron repulsions that weakens your attraction, right? Because it's Z minus S minus R, that repulsion factor will be bigger. So since that's bigger, it's going to decrease your effective nuclear charge. So this one, okay, oxygen, in this case, will have a stronger attraction than oxide because it has less electrons and weaker electron-electron repulsions. Okay, so that's how you go through that list there. But it's in order from most to least significant, really important. So, final slide In summary, moving up or down a group, you focus on principal quantum number, number of electrons, number of energy levels only. I'm not trying to be dramatic here, but no one cares about anything else. Don't include it in your answer. I don't want to see it there, okay? Include all the other stuff in your answer if you're focusing on moving across a row or a period. That's where your effective nuclear charge, Zeph, dominates, okay? Shielding is the same, and the repulsions don't matter that much, but how the protons differ will make the most difference. You saw in the previous slide here that once you get past the number of protons in the nuclear charge, then you can focus on the other things. Okay? Use that list. Can't go wrong. Use it to explain everything. Okay? Ionization energy, atomic radius, you know what I mean? All that stuff comes right back to attraction and Coulombic, Coulomb's law. All right, guys? Hope this helped make have some of that stuff make sense, and we'll take it from here. All right? Thank you.